Alright, so this video is about curve sketching. And in curve sketching, we're basically drawing graphs of these polynomials using calculus. And yes, we can use calculators for it, but we want to focus on details as exactly as possible, where calculators are more approximations. But and we may still use approximations. There's nothing against approximations. But if there's a need to find things exactly, we can. So anyway, so it's several guidelines to curve sketching. And these are some general guidelines we follow. A, find the domain. You don't have to follow any of these guidelines. These just give you a place to start so you can get going until you find out what the curve most likely looks like. So you can skip any of these, go in order that you want. It just gives you ideas where you can start and help you start in getting the graphs without depending on a calculator. All right, so the next part is find the X and Y-intercepts. You want to determine, is it symmetric about the y-axis? Is it symmetric about the origin? Is it symmetric about some other number? Generally, y-axis and the origin are probably the only place you really need to know whether it's symmetric about it. What are the asymptotes? If it has any asymptotes. It may not have any asymptotes. Does it have any intervals of increase or intervals of decrease? And I'm about to clear the screen, so be sure to pause the video and get these down, because I'm about to clear the screen. Does it have a local max or a local min? And finally, the last one, where are its points of concavity or inflection points? And I never really get here. I never really get to the place where it's asking about concavity. It might have inflection points, but I never really get this far. Before I get this far, I generally have enough information to sketch the graph. All right, so about to clear the screen. Now let's actually go to some examples. All right, our goal is to sketch this graph. So start off with our guidelines. So I listed all the ones I usually go by. I didn't bother writing G, which is concavity. I think I can get it without that much information. And again, you don't have to go in this order. You can skip about any way you want. So the first thing I have is domain. So to find this domain, you basically want to find out what x cannot be. If you got some polynomial like y equals x squared plus 1, well, x can be anything. So this domain is all red numbers because there's no number you cannot plug in for x. That makes it undefined or imaginary. So some functions, x can be anything. In this problem, there may be numbers x can't be. For example, my denominator is x squared plus 9. If I set that equal to 0, x squared plus 9 equals to 0, I'm going to find that it has to be imaginary. Like once I subtract 9 from the other side, I'm going to get x squared equals to negative 9. And you can't square a number and get negative 9. So you can't find any numbers that can be vertical asymptotes. And you have no numbers that are excluded from your domain. So my domain is all real numbers. So my graph goes on from left and right forever. All right, so next thing. And again, the reason why is there's no numbers that make this graph undefined or make it imaginary. Like I don't have the square root of x any place. So I can't make it imaginary, and I can't make my denominator 0. It's impossible. So that's why. And going on to the next thing, X and Y-intercepts. So X-intercepts, you just simply set the y equals 0. The Y-intercepts, you place x to be 0. So let's find the Y-intercept first. I'm basically replace all the x with 0. So my Y-intercept should wind up being y equals to 0 over 9. So that's 0. So my Y-intercept is 0. And my x-intercept, when I make y equal to 0, I will get 0 equals to x squared over x squared plus 9. So to solve that, I cross multiply x squared plus 9 to 0. So you would still get 0 equals x squared. So x has to be 0 because 0 squared is 0. So my x-intercept is also 0. Once I start finding information like that, I'll start plotting it so I can have that information down, because soon I can get enough information, I can graph it. So I know one place on this graph is 0, 0. So I know that's one important place on my graph. So x and y-intercept there. That's 0. And symmetry. Symmetry is found this way. Basically, symmetry means that if f of x equals f of negative x, then it's even, It's an even function, and it's symmetric about the y-axis. That means if I plug in a number for x, and I plug in a negative number for the same x, I will get the same output. That means it's an even function and symmetric about the y-axis. And if f of x, or better yet, if f of negative x equals negative f of x, then it's odd, and it's symmetric about the origin. So odd function means it's symmetric about the origin. Basically, that means if you rotate it 180 degrees, you get the same picture. A perfect example of that would be, say, a curve like this. If I rotated this curve 180 degrees, so this would be 90, and this would be another 180, I want to get an exact same curve. So, or rotate it forward, 90 and then 180, I get the same curve. So we say that's symmetric about the origin. And again, symmetric about the y-axis basically means it's a mirror image about the y-axis. So if you folded a crease down the y-axis, both sides lie on top of each other. So that's what we mean by symmetric, and this is how we can prove whether or not it's symmetric. That could be useful. All right, let's go. Even though it could be useful, it's not something I personally look for right away. So I'm looking for other things. For example, the asymptotes are really useful for me. So if I want to find asymptotes here, I know there's no vertical asymptote because you can't make the denominator 0. So I know there's no vertical asymptote. However, there's a horizontal asymptote. How I know this is, if I look at the limit as x approaches infinity of this function, well, the limit of numerator goes to infinity, the limit of denominator goes to infinity, so that means I can use L'Hopital's rule. So that means that the limit as x approaches infinity of this function is 2x over 2x, which is 1. So I know I have a horizontal asymptote at x equals 1. I'm going to put my 1 right here, and I know that this is a horizontal asymptote there. So that's nice to know. To me, it's pretty important to know. The next thing I want to look for is, I'll probably look for local max and local mins. So if I had that function, I want to find out if it had local max or local min. So I'm skipping ahead to f. Intervals of increase and decrease is going to be important too. Come back to that one next. First I'm going to f. I'm going to need more space, so I'm going to erase some of the stuff I've already written. So hopefully you have it all. Alright, so local max and min. We learned in the previous lessons that we could find local max and min by taking the derivative of that function. So y prime, that function involves quotient rule. So it's going to be low times the derivative of high. Well, so again, low times the derivative of high. Subtract high times the derivative of low, all over low squared. So if I simplify this, see both of those got 2x in common, so I can factor out a 2x. So I can call that 2x. What's left is going to be x squared plus 9, subtract x squared, all over x squared plus 9, quantity squared. So I can see right now that these cancel. So my numerator is now (18x), and that's going to be over x squared plus 9, quantity squared. So that's y prime. So if I want to find my local max, I can set that equal to 0. So I'm going to set 18 over x squared plus 9, quantity squared equals 0, because I'm looking for horizontal tangents. So when you solve that, basically this bottom denominator times 0 gives you 0, so it's going to be 18x equals 0. So x has to be 0. So this is also a local max or min. Local max or min. Since this is an asymptote, I'm getting a good guess it's most likely the local min. It's probably going to bend downwards. But I want to know the interval of increase and decrease to make sure I'm right. So I'm giving it a guess. I'm thinking it's going to be a local min because it just looks appropriate. I really couldn't have an asymptote down here, or else we have another local min. So like, it couldn't do this, the asymptote added later, or else our math would have showed us the other local mins or local maxes. So it most likely only has one local min, so most likely it does that. But let's see. Let's find intervals increase and decrease. Now I can know for certain. All right, so the last thing I think I need is intervals increase and decrease, and using the fact that we knew our derivative was there, 18x over x squared plus 9 squared. I can find my interval increase and decrease. Since this must be a local max, local min, I can see what's happening to the left and right of it. So on the left side of it, I could plug in a number, that's 0. So on the left side of 0 is negative numbers. So I can plug in like negative 1. Y prime at negative 1 is going to be negative 18 over 10 squared. This is negative. Because that's negative, I know it's decreasing. So I know it's decreasing. All the negative numbers, basically when x is less than 0. And if I try the positive number, so y prime at positive 1 to the right side of 0, I will get 18 over 10 squared, right? Because 1 times 18 is 18, and we already know 1 squared plus 9 is 10. So this is positive. So I know that on the right side it's increasing. So it's increasing. X is greater than 0. So I know my function must be this. It must fall to get to 0. Then at 0 it starts rising. So I got enough information without using the fact that it's symmetric about the y-axis, because it is. I could have proved that. And I didn't have to prove that it was concave up or concave down on inflection points. I have a sketch of the graph. And just to prove it's symmetric about the y-axis, because I didn't talk about symmetry at all, just for the record, the original function was this: y equals x squared over x squared plus 9. And to prove that it's even, alpha of x has the same thing as alpha of negative x. So basically, if I plug in alpha of 1, it has to be the same thing as alpha of negative 1. So alpha of 1 in this function would be 1 over 10. Alpha of negative 1 in this function would be 1 over 10. I didn't show the math for it, but you plug in 1 there and 1 there. 1 squared is 1. So anyway, it should be 1 over 10. So it is even, because alpha of 1 equals alpha of negative 1. So it is even, or symmetric about the y-axis. Symmetric about y-axis. So yeah, it should have been a mirror image about the y-axis. Could have been a better mirror that I drew, but it's a good sketch of it. So anyway, that's curve sketching. I could do a lot more of them, but since they all work the same, you're going to follow those steps and use the information that you have to try to come up with a sketch of the graph. Some of them get really, some of the steps get really complicated, so you might not want to actually try to use that step. If you don't like it because the algebra is too deep, or you just don't want to do that step, you can skip it and see if other places will help you find the sketch of the graph. At some point, they're going to ask you about finding slant asymptotes. And just so you know, I want to tell you about slant asymptotes right now. So you only have slant asymptotes if the degree of the numerator is exactly 1 larger than the degree of the denominator. If that is true, you will have a slant asymptote. How you find it is you use long division. Systematic division does not work with slant asymptotes usually. So it's best to always use long division. If you do the math of long division there, x times x gives you x squared, x times negative 12 gives you negative 12x, and you wind up having to change the signs, give you 12x plus 12, and then you have to add 12. So distribute it again, you get 12x, subtract 144, change the signs, and essentially you get a remainder of 156. So your remainder would be 156. The slant asymptote is everything but the remainder. So my slant asymptote for this one has to be slant asymptote. Has to be y equals everything but the remainder, so all of this, x plus 12. So that's my slant asymptote. Meaning I got a y-intercept of 12, I'm call my 12 here, slope of 1. So say this is 1. Rise 1, run 1. So I got a point around there. That's enough. Come up with my slant asymptote. You got a vertical asymptote in this one. Should be positive 12. So I could graph that someplace over here. And I could again trying to find out other information to help me graph it. Anyway, I just want to review how to find slant asymptotes. That's all I have. Good luck.